All right. So next we move on to a very interesting topic in sampling. The goal over here is what? I'm going to take a continuous signal. I'm going to sample it. I'm going to get a bunch of values, samples. And then later on, I'm going to be interested in reconstructing the signal with the samples that I have. Why is sampling a good idea? Oh, if you guys have heard me talk about the sampler in a restaurant, you guys, this is going to be a repeat discussion. Why is sampling a good idea? Why not have all the, go ahead. Right. So a lot of values that are not adding to my information, they are redundant. And I'm going to have to store them. I'm going to have to process them, and I don't even need them. So why have them, right? So I'm going to go with limited amount of information, limited number of samples, but I need to be careful about that. I can't go below a limit, not the Nyquist limit. It is like the sampler that you find on a menu on a restaurant, right? Like if you want to find out how good or bad a restaurant is, you will go say order their sampler, some sampler. You will not have all the dishes over there. You will have some dishes, right? Because if you had too many dishes, what is going to happen? Well, if you eat all of them, you're going to have to store, process a lot of it. Yeah. So there's no need. You have some of them, and you have a pretty good idea about whether the restaurant is good or not. And it's going to be expensive. And it's going to take you a very long time to eat all of that. Yeah, so it's going to be delays, right? Lots of things to process. It's going to increase latency. So sample it, choose specific values. Then the question is what? Can I go very few, or can I go take a lot of values? In other words, can I undersample a signal, or can I oversample a signal? Well, if you sample right at the edge, which is the Nyquist rate, then you will be, that is just enough. If you go too high, then you are trying to get oversample. Too many samples. Don't need that. If you go lower, then what that means is you will not be able to reconstruct the signal from its samples. So let's try to see where this comes in. You have a analog sensor, right? Some transducer, some microphone giving you x of t, a continuous time signal. We are going to sample it, and there are several ways to sample it, to get xp of t, a sampled signal. And we are choosing a sampling frequency of omega s, or we can actually call this fs, right? Fs is going to be what? Omega s divided by 2 pi. The difference is one is it in hertz, the other one is in radians per second. Omega s is going to be 2 pi divided by t. So can I say that t or ts is going to be my sampling time? This is essentially the resolution I have in the time domain. Resolution in time domain. How close are my samples? Or how far are they? That is set by cap t. Cap t controls fs. What is the relationship between fs and cap t? Right. What is that? 1 over t, right? So when you multiply, when you sample the signal, what do you get? You get a value at t, 2t, 3t, 4t, 5t, and so on, right? Integer multiples of cap t. That's where you will get your samples. You will do whatever you want with them. You will process them, you will send them, you will do all of those things that you wanted to do with those samples. But at the very end, suppose you want to hear them. You want to hear them, you have to reconstruct them into an analog signal, a continuous signal to hear them. So how do you reconstruct? Well, you had some samples. Let's try to reconstruct some XR of t. And if it is, the question is it the same thing as you started off with or not? So the basic problem is, first, how can you represent the signal completely with a unique set of values, unique set of samples? And how is the reconstruction step going to look like? Let's take a look at that with your ideas for reconstruction. I want you guys to think about, what is that? Filter it? Oh, okay, filter it. But don't even think about filter. You are a layman now, right? Assume that you don't know anything about filters or anything. You are just given these values, and you are given that this is a sampled signal. So you are given x of nt, the values of in x at t, 2t, 3t, 4t, 5t, and so on. The x-axis is time, the y-axis is the value, and it is tracking the signal x of nt, and is an integer. Right? So those are the values that are given. How would you reconstruct the signal? So your goal is, you are given a set of samples, how do you make it continuous? What is that? Connect the dots. Let us use blue for that. Connect the dots is option number 1. Yeah. Okay. Connect the dots is pretty good option. I'm going to call that with a name. I'm going to call that linear interpolation. I'm interpolating the points in the middle of those two red dots, and I'm doing that linearly. Linear interpolation. Linear interpolation is also called now filter, first order filter, first order hold. Linearly, right? It's not quadratic, it's not cubic, it's a linear increase between a point and another point. Some other option. Connect the dots is one, that's called linear interpolation. First order hold. If there is first order hold, there is also zero order hold. How does zero order hold look like? That's the same value, sample and hold. Hold it. Hold it until you get the next value. I will hold it until the next value. Let me try. Okay. Keep it the same. Next value I got, keep it the same until you get the next one. You get the next one. Didn't want that to happen. Oh, all right. No. Yeah. All right. I think this will work. Oh, next value I got. Next value I got. Next value I got. And that. Right. So that's called zero order hold. It's going to give you a staircase like waveform. Staircase waveform. Are realistic signals like this? Are real signals linear or staircase like? How are real signals? Smooth, right? So if you want a smooth thing, what kind of interpolation technique can you do with this? Oh, go ahead. So there's no quadratic. You could do quadratic. You could do a polynomial based interpolation, but there's a standard interpolation technique called sinc interpolation. So all you do is you superimpose a sinc on each of those samples and add everybody up. So let's take a look at that. I'll do that in black. I will say this is going to be my sinc interpolation. Sinc interpolation is also called ideal. Sinc interpolation. Ideal reconstruction. You see what I'm doing here? I am multiplying each sample with a sinc. What is the amplitude of a sinc function? 1, right? Where it peaks, right in the middle, it's 1. So I'll multiply each sinc with that particular red value. So when I do it for the first sample, I get this. Notice how I am crossing the zero. Where am I crossing the zeros? exactly where I'm sampling next, right? So this sinc, in other words, all the sinks, the samples are not contributing to others. You see that? So when I do the multiplication with the second sinc, how is it going to look like? This guy will go down, it'll cross 0, and then it'll go like that, and then there, and then there. And then this guy is going to cross 0 at 3t, there, and there, and there. So each sample that I'm taking, when I try to reconstruct it, that sinc, each sinc, when you add it up, this particular value, no matter how many samples you have, will only have one contribution from this. All the other sinks at that point would have been 0. You guys see that? Now, you add all of these sinks up, what do you get? You get something like this. A little bit of a smoother function because of that sinc being smoother. Sinc interpolation, ideal reconstruction. Why is it ideal reconstruction? Because it is a sinc function in time domain. What does that mean for our reconstruction filter here? Rectangle, what is it? Low pass filter? Ideal low pass filter. When you do an ideal low pass filter, brick wall filter, that's why ideal reconstruction, all you're doing is you're doing a sinc interpolation. You're taking each sample that you have, you're multiplying it with a sinc, and you're adding all of those sinks. They are all spread out in time, right? The sinc is centered at t, 2t, 3t, and so on. But the reason it works is because each sinc is orthogonal to the other. It's only contributing a non-zero value to only one sample. All sinc 1, this guy doesn't contribute any value to the next one. It is 0 over there. All right, questions about these three ideas? We will be looking at each of these three reconstruction techniques in detail today. All right, so let's talk about Nyquist now. The question is, can x of t, the continuous signal, be represented uniquely? Uniquely, it has to be unique. Let us try to demonstrate that uniqueness here. Let me copy this. And let me paste it over here. Let us say I started off with the same samples. My correct answer was this, right? Something continuous like that. Not the correct answer, assuming that it was enough. It was that. But it is possible that our signal did this. Let's take it in red. No, let's do it in blue. It is possible, right? It's same samples, exactly same samples, but it's completely different. Why? This is not going to be. So what did we do here? We undersampled the signal. We had to try to sample it much finer, but we didn't. We sampled it less than what was required, which is why we would not reconstruct this signal. We actually would reconstruct this signal, something else, slower, right? Which means that the sampling rate, the space between these is going to be related to the frequency of the signal if you want to guarantee that you will be able to reconstruct it back properly. Do you see that? So can you reconstruct it over here if you had those? No, you can't, right? It's not enough. You undersampled the signal. So what does that mean for TS, sampling time? You have to reduce sampling time. For sampling frequency, you have to up the sampling frequency. So here you have these samples here. This is the amplitude here is what? This is x of 0t. This is x of 1t. This is x of 2t and so on. So the question is, can you reconstruct the signal? Maybe it is the dotted line, or maybe it is something like this. In one, we are doing a proper reconstruction. We had enough samples. In the other, we didn't. So what is the question here? Can you represent uniquely by a sequence equally spaced samples? Can you uniquely represent x of t? Well, uniquely no, right? Because this could be a signal like this, or it could be a signal like this, as long as it's passing through those points. So no, in general, unless we sample it at an appropriate frequency. Sample it faster, increase omega s, which means that we are, or disallow fast changing signals. Only allow slow changing signals to go through this sampling process. All of this to say that the frequency in the signal that you're trying to sample is going to matter a lot. And we have a rate, Nyquist rate, which means that if you want to be able to reconstruct, you need to sample at least twice the maximum frequency of a signal. So let's try to take a look at a Fourier transform here. This is for some signal x of omega. Its Fourier transform looks like this. This is at baseband. Maybe it is, say, voice signal. So voice signal, when you take a Fourier transform of it, it goes from about 200 hertz to about 4 kilohertz, right? That's in frequency. So if it were voice, it would be 200 hertz to about 4 kilohertz. And you can multiply by 2 pi to get it in the frequency domain. So you get to get it in omega. So that would be what, 400 pi to 8 pi kiloradians per second, right? So that is defining omega m, the maximum frequency component in the voice. And if you want to sample that voice and be able to reconstruct it, right, you need to sample at least twice the maximum frequency. So 8 pi k radians per second is the maximum frequency. Sample it twice. 16 pi kiloradians per second is the least rate at which you can sample. You have to sample more than that. Also, the signals have to be band limited, right? What if there is no band limited? It's omega m. So for voice, I can say, yeah, my voice is limited to 4 kilohertz. But there could be signals that may not be band limited. Think of an example. A sinc, is a sinc band limited? A sinc in frequency, is it band limited? A sinc goes on forever, right? So sinc is not band limited, which means if you have a signal which is a perfect square, perfect rectangle, a pulse, perfect pulse, then in frequency it is never going to be band limited. It's going to have all the, because of that discontinuity, you have all the signals, right? So it's never band limited. So finding out that omega m is not going to be very appropriate. So then what do you have to do? You have to do some trade-off. What is that trade-off? You have to say, all right, here I get almost 90% in my 95% of my energy is at until this omega m. I'll take that as my omega m and work with that. So the result in time domain for that is going to be the rectangle is not sharp, it sort of has a roll off. Right? So being band limited means what? After a certain frequency omega m, everything is zero. Right? It's limited in its band, in its spectrum. So in this case, it is band limited between minus omega m and omega m, the way we have sketched it. So it is zero beyond that. Things can be limited in time as well. So you can have time limited or you can have band limited. You cannot have both. A signal, if it is time limited, limited in time, it is going to be band unlimited, right? So if you have a rectangle in time, you have a sinc in frequency, goes on forever. If you have a sinc in time, you have a rectangle frequency. So if you can have limitation in one or the other. The examples of band limited signals, the ones from your telephone or your voice, all of these are band limited signals. And if you're not able to find that band limit of the band, you do some approximation in terms of how much energy is in that particular band, say 95% cutoff, 90% cutoff, and so on. Okay, next, let's take a look at ideal sampling. Ideal sampling is nothing but multiplying a continuous signal x of t with a impulse train. Impulse sampling or ideal sampling. Multiply x of t with impulse train. In which domain are you trying to multiply? Time you are multiplying. What does that mean in terms of frequency then? Frequency convolution with what and what? X of omega with what? The Fourier transform of an impulse train is an impulse train. So you're trying to do a convolution of X of omega with another impulse train. This is sort of the entire discussion here. That's it. That's the whole topic. So let's try to look at it in terms of their mathematical expressions. So you have X of t over here. You are multiplying with an impulse train. What is the time period of this impulse train? Take a look. Cap t, right? Because you see, n is going from negative infinity to infinity. You are getting t minus 1t, t minus 2t, 3 minus 3t, and so on. So you're getting an impulse at 0, t, 2t, 3t, and so on. So the time period of this impulse train is t. So we have this impulse train. We have sketched it over here, represented it over here. What would be the Fourier transform of this guy? Anybody remember? All right, give me the Fourier series coefficients of this. AK. What is AK for Fourier impulse train? 1 over t, right? Because time period is t. So what is the Fourier transform of the impulse train? Let's try to find that out. I remember it as 2 pi. There will be a summation over all k, followed by AK, which is 1 over t, followed by another impulse train. This is going to be at omega minus k omega naught. Can you guys tell me what omega naught is going to be? Two pi divided by t, right? Time period is t. Omega naught will be 2 pi divided by t, right? So you can put that in here. So let me just do that here. And I can actually bring this out here. Instead of saying k 2 pi t, I will just say omega minus 2 pi k divided by t. You guys okay with that? That's the Fourier transform of your pulse train, right? Sorry, impulse train. Next, what are we doing? We are multiplying x of t in time domain with p of t. So xp of t, the sampled signal is the product of x of t and impulse train. X of t remains as is. The impulse train is written as a summation of the impulses at t, 2t, 3t, and so on. We did that. What is this? This is a function in time multiplied with the impulses. You essentially evaluate that function at those times when the impulse is valid, right? So you have summation over all n x of nt multiplied by the impulses at 1, t, 2, 3, 3, and so on. So what is this going to look like? Well, this is going to look like all of this got multiplied with this to give you this, right? You still have impulses, but their locations are at 0, t, 2t, and so on. Their values, their amplitudes are going to be x of 0t. This will be x of 1t, 2t, 3t, and so on, right? So only the weights of the impulses have changed because of that. All of this is the time domain view, right? So we are over here in all of this. I don't know about this yet. Questions about this slide? Take the signal, multiply it with the impulse train to get another impulse train, but those will not have impulses with a weight of 1. Now you have impulses with a different weight depending on the signal that you sampled. Next, the frequency domain view. And you guys were quick to say that if you are trying to multiply in the frequency time domain, you are convolving in the frequency domain. And we also cannot afford to forget about that 1 over 2 pi factor. So let us suppose that I am band limited, right? I am band limited. So in frequency, I have a limit, plus and minus omega m. What kind of signal is this? It is a band limited signal, but can we say anything about the shape of x of t? Sinc squared, perfect. You guys have become so good at this. Yeah, it has a sinc squared shape. Next, x of omega is a triangle. It is band limited to omega m. What did I do in time? I multiplied in time a signal, a sinc squared signal with an impulse train. That's what I did in time, right? In frequency, what does that translate to? It translates to taking this triangle and convolving it with the impulse train. Another impulse train in frequency, right? So this guy gets convolved with this. So what is P of omega going to be? Well, you're trying to find the Fourier transform of an impulse train. The Fourier transform of an impulse train is right here. You can see that 2 pi divided, we did this. I used the Fourier series coefficients and I found the Fourier transform of this guy. So I'm just using it over here, where omega s is what? 2 pi divided by t, right? So t is right here. Yeah. And I'm calling that omega s, the separation of those impulses, as omega s, 2 omega s, minus omega s, and so on. So another impulse train in frequency, and I'm finding that omega s as the 2 pi divided by t, where t is your sampling time, omega s is your sampling frequency, right? So when you convolve this with this, what do you get? You get that, right? This triangle is going to move here and here and here, here, all of these, right? The scaling will also be 1 over 2 pi, which is not a big deal. You have a amplitude of 1 over here, you have an amplitude of 2 pi divided by t here. Because of this 2 pi and this 2 pi, they get cancelled, you will be left with 1 over t eventually, right? So that 1 over t carries over. And then you, because this guy was band limited to plus and minus omega m, what do you have? What is this point? Omega m, right? This was omega s, because that was the set by the time period of the impulse train, right? 2 pi divided by t. So what would be this guy, this point? Well, that would be omega s minus omega m, right? Let's see that how we are, and then you can, similarly you can find out what this is, what this is, what this is. You can find out all the points. You need omega s and omega m. Where is omega m coming from? It is coming from the highest frequency in the signal that you're sampling. Where is omega s coming from? It is coming from the how far the impulses are in your impulse train. Now, if three things can happen over here, three things can happen. Try to compare this with this. You can have, let me zoom in here. You can have this to be higher than this, right? So you can have case one, let's write it in red. Case one, you can have omega s minus omega m greater than omega m. What does that imply? That implies that omega s is greater than 2 omega m, right? So when omega s is greater than 2 omega m, your triangles are disjoint. And there is no overlap. There is no corruption of the high frequency components in my signal that I sampled. So you don't lose them. So this is when you're more than 2 omega m, this is called oversampling. You have enough samples. So what would you do for reconstruction? Well, you just put a filter here. You got the signal. You started with a triangle, you have a triangle, right? So you can do the filtering and you will be able to get it. So when you oversample, you will be able to get the reconstructed signal. You will get it. But can I afford to go very, very high? What is the problem if I go very high? omega s is greater than 2 omega m, it is like 10 omega m. What happens then? Well, the triangles will be very, very far away from each other, right? So if the triangles are very far away from each other, depending on the filter that I designed to reconstruct, I may be allowing all the out of band noise to get through, right? Which I don't want. So I want it to be close. What is the limit? Well, they can touch each other, right? So touch each other is what? Case 2. Case 2. What would that be? That would be omega s equals 2 omega m. The sampling frequency is exactly twice the maximum frequency of the signal that I sampled. This is called Nyquist rate. Nyquist rate corresponds to how many samples in one time period. Suppose you have a cosine, right? That's one cycle, up and down, right? That's one cycle. How many samples should you have in one cycle to be sampling at Nyquist rate? 2, right? So if you have 2 samples in one time period, you are good. There is a problem. Where are the samples? Because if I pick the samples at zeros, I can't get the signal. If I pick the samples to be the peaks, I got it, right? Close to it, not exactly, but close to it. Let's go. Case 2, twice the maximum frequency, exactly at Nyquist rate. But in this case, I'm playing a little bit risky, right? Because these two are just touching each other, which means that there is a lot of pressure on the filter. What is the third case? Omega s less than 2 omega m, undersampling, leads to aliasing, which means corruption of the high frequency components. How is that going to look like? Well, it's going to look like this, right? So you see what happened here. The high frequency components, no matter where you filter now, you had corruption in the high frequency components of the signal that you sampled. So low frequency components you will be able to hear smoothly, high frequencies will get distorted. That's called aliasing. That happens when you undersample the signal, not enough samples. Questions? When you sample the signal, view in time domain, view in the frequency domain. And why is Nyquist, right? This proves Nyquist criteria. All right, let's take a look at Nyquist sampling criteria. You have this band limited signal x of t. We are assuming that to be a triangle. You have multiplied with an impulse train, which meant that in frequency you convolve with another impulse train. Then you want to design a reconstruction filter at the end, right? Once you get a sampled signal, you want to reconstruct using some h sub r of omega. So we already looked at the Fourier transform of the sampled signal, xp of omega. We already looked at that. We talked about what happens when these 2 points are away from each other, touch each other, or when you have aliasing. But here we are talking about how do you design h sub r, right? H sub r, if this is the ideal filter, so you wanted this, right? If you want this, you just make a ideal low pass filter over here. How would you choose omega c? Well, omega c, the cutoff frequency of your ideal low pass filter, should be more than omega m, but it should be less than omega s minus omega m. So you can conveniently choose that to be half of the sampling frequency omega s. If you do, and if this height is t, then you will get exactly the gain of your low pass filter is over here t. If you do that, when you multiply in the time domain, your reconstructed signal in the frequency domain is going to look exactly the same as what you had transmitted. Right? So choose sampling frequency such that omega s is greater than 2 omega m so that you don't have aliasing. Choose the cutoff of the reconstruction filter such that it is more than omega m but less than omega s minus omega m. Because you don't want to bring this in, right? You want to be as close to omega m as possible. Because even if you go here, you are letting out of band noise to get through, right? So suppose you had some noise here. Let me pick a some noise here will get through, which we don't want. So you want to be as tight as possible. So again, the trade-off between quality of your reception and the cost that is related with the filter design. Let's see. We have a few more minutes. You guys are packing your bags already? All right. 4 more minutes. Oh my gosh, raised eyebrows. All right, let's see. Nyquist cyclic criteria says you need to, in order for you to be able to reconstruct the signal, you need to sample at twice the maximum frequency of the signal. Choose the sampling frequency greater than twice the highest frequency in the signal. There are many frequencies in the signal. Find the highest one, twice, sample it more than twice that value. Nyquist rate is twice the maximum frequency. That is a limited value. You can be at Nyquist or greater. You cannot go lower. So suppose we sample exactly at Nyquist rate. We are sampling the signal exactly at twice the maximum frequency. What does that imply? That implies that omega s should have been greater than 2 omega m. What does that imply? That implies omega s we know is 2 pi divided by ts, right? Where ts is what? The sampling time. So it's the time period of that impulse train that you are multiplying it with. This should be greater than 2 times omega m. What is omega m? Omega m is the highest frequency component, which corresponds to 2 pi divided by Tm. What would be Tm? Tm would be the time period of the highest frequency component in the signal, right? So there are several frequencies in the signal, ranging from 0 all the way up to omega m. The time period that corresponds to the highest frequency omega m, that is going to be your Tm. It's not a periodic signal. I'm just saying that particular frequency has certain time period. That is going to be Tm. So if you look at this, what is the relationship between Ts and Tm? Omega s should be greater than 2 omega m, but in time, it is slightly different. Ts should be less than Tm divided by 2. So the sampling time should be smaller. The sampling frequency should hence be greater. So thus, to recover the signal, we should have more than 2 samples per period of the highest frequency signal, right? So suppose you have a cosine which only has one frequency, in this case omega m. The question is, where are you going to sample it? You can sample it here and here. That is 2 samples in a period. Can you reconstruct the signal with those 2 samples? No. Your reconstruction signal will look like what? A line, right? Which is not cosine omega mt, right? So, okay, I can't take those 2 samples. Where should I take those 2 samples? I can maybe take something like this. Well, if I take that, this is still 2 samples. What do I get here? I will not get that. I will get, well, if I did sinc interpolation, it will be a little bit smoother than that, but it is still not cosine, right? It is getting close to it, but it is not cosine yet. The way I get cosine is if I sampled here and here, right at the peaks, and I do sinc interpolation, then I will get my cosine signal out. All right, 12:05. Let us stop over here. I will see you guys for the exam on Monday. I will send out a Piazza note describing the logistics, the topics, the lectures, the homework, whatever is going to be on the exam. But if in case you missed it, we don't have time slot 2, we only have time slot 1, and we get done with the exam. No multiple versions. It's going to save a lot of time and energy for me as well as the TAs. All right. We adjourn. Have a good rest of your week. Enjoy your weekend.